This is 2018 USAJMO problem number 1, and here is a view of this rather easy problem, actually, combo problem. For each positive integer n, find the number of n-digit positive integers, n digits, that satisfy both of the following conditions. Two conditions given. No two consecutive digits are equal, the first condition, and the second condition is that the last digit is a prime. Well, the second condition is particularly easy to handle, I would guess, right? So really there's only 4 prime digits, 2, 3, 5, and 7. So really we have 4 choices for the last digit. The digit to the left of that number would have 9 choices only, noticing that you can't have 2 consecutive digits that are equal. Once you know what that last digit is, then you have only 9 choices for the previous digit. For instance, if your last digit is a 3, then the previous digit is anything but 3. So, and then you keep going on and on, counting by nines. Let's do an overcounting, strategically overcount this. So we say 9 choices for the digit before that, and let's ignore the fact that the first digit cannot be a 0, and let's assume we said there is 9 ways to choose the very first digit as well, right? So first digit from the left side. Well, we can easily adjust it, right? So to solve this problem, let's make the following notation. So let's say that the number of n-digit positive integers which satisfy this condition is a sub n. Right, so a sub n is the answer if you have an n-digit number, right? So the way we counted here, this count over here, which is 4 times 9 to the power n minus 1. So 4 times 9 to the power n minus 1 is equal to, well, we started out as with a claim that we will count the number of numbers of a sub n. However, we also inadvertently counted something else. We counted also numbers that could potentially start with the digit 0 as well, and they are definitely not part of a sub n. But if there's a 0 on the very first digit, then the second digit is guaranteed not to have a 0, simply because of that first condition, right? So by virtue of a number being a number, the first digit cannot be a 0, but if the first digit by mistake is a 0, then the second digit by virtue of that first condition is definitely not 0. So therefore, because you have a non-zero entry on that second digit here from the left side, then that's pretty much it. So this is just the way when you reinterpret that number, excluding the very first digit, which is a 0, it is a sub n minus 1. So in a sense, we did a case work, right? Case work based whether on the first digit is a 0 or not. So we are reinterpreting this as a sequence of numbers. If the first digit is a 0, then the remaining n minus 1 digit number is just a representation of a sub n minus 1, meaning an n minus 1 digit number which satisfies these two conditions. Or versus if the first digit is a non-zero thing, so this plus sign here represents a case work. Then we have a legitimate way to count this a sub n thing, and that's it. So therefore, that would be a recursive formula to calculate a sub n. And if you are not happy with this, we might as well just rewrite it in the following fashion. A sub n is simply equal to 4 times 9 to the power n minus 1 minus a sub n minus 1. So we are pretty much done with the first part of the problem. Now for the second part is to come up with a closed form formula for this, right? Like in any other recursive formula, when we want to derive it, it might be a good idea to start with checking a few initial conditions. For instance, a sub 1, one-digit number which satisfies these two conditions. You would admit it's just, there's 4 ways to do that, right? So it's just the numbers 2, 3, 5, or 7. If it's a 2-digit number, it's slightly more, right? So probably we don't need it if we are to find in this particular case, but regardless, just to check if our formula makes sense, let's count it independently. So if you have a 2-digit number, its very first digit is going to be either a prime or a non-prime, so it's tens digit. So and based on that, we can count a sub 2. We know that the last digit has, regardless, it's one of the 2, 3, 5, or 7, but the tens digit is kind of interesting. So if the tens digit is a what? Is not prime, not prime. Then the second, the units digit is not affected by that first condition. Well, how many choices of not prime do we have? Well, not prime means 1, 2, 3 is not good, 4, 5 is not good, 6, 7 is not good, 8 or 9. We have 9 choices here. So for this one, the very first digit we have times 9 times, and the units digit we have 4 choices. So that, so what am I saying? Not times 9 times 1, 2, 3, 4, 5 choices. So in total there are 20 ways to do it if the tens digit is not prime. If the tens digit is prime, we have 4 choices of a prime, then the units digit will be 3 of the remaining primes, right? So it's really 4 times 3, 12 more choices, right? So if it's a prime, and the second case will produce 12 more. So when you add them up, so we have 32, basically. Two-digit numbers which satisfies these two conditions are 32 of them. And so that's pretty good. Let's check if our formula gives that. So if we calculated A2 from our formula, that would have given us 4 times 9, 2 minus 1 minus, I'm at a hotel lobby, so there's some sound coming. A sub 2 minus 1 is A sub 1 is a 4, and indeed that is just 4 times 9 to the power 1, which is 9 minus 4, and that's 36 minus 4, which is a 32. That's pretty cool. So we have the same answer. So we're very confident that our recursion works. Now we can easily start the second step. For the second step, there is a couple of different ways you can solve the problem. Oh, before I go to the second step, there's an alternative way to create a recursion for this problem, and it is based on, instead of making the analysis based on the very first digit, we can make it based on the second digit next to the first digit. Let me first show you that trick as well, or that derivation as well, and then we can move on to the to find a closed form formula. So basically, again, let a sub n represent the same thing, n digit numbers which satisfy those two conditions given in the problem statement, right? So I won't bother writing that full definition again. But then, like we said, so we have our n digit number, dot, 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 dot. Last digit is a prime. Fine, but I'm interested in, so we have our first, second, third, and so on. So I know that's not the proper way to count the digits, but fine. So I'm considering this digit over here. Depending on whether this digit is a 0 or a 1, right? So we should be able to again derive the desired formula in the following sense. If it is a say a 0, let's start with the case if this is a 0, then the right hand side, the number to the right of that 0 is an n minus 2 digit number, and besides, because the second digit here is a 0, it starts with a non-zero number here, so you have a legitimate a sub n minus 2 n minus 2 digit number which satisfies the two conditions of our problem. But we still have a choice in terms of selecting the very first digit here, but because this one is a 0, this one cannot be a 0. Hey, it couldn't have been 0 anyways, right? Because it's the very first digit. So there's really 9 choices for that one. That is correct, I think. Or the second case would have been that again 3 dot 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 dot. Again we have a prime here, and minus 1. So the third, the second. Okay, so the second digit from the left, this time it's not a 0. So if it is not a 0, then the whole number here, okay, maybe I should do it the other way. So this whole number, because this is a non-zero digit, this whole number is a legit a sub n minus 1 digit number. And now, how many choices do we have for that very first digit? Well, the very first digit cannot be 0 because it's the very first digit. And secondly, it cannot be the number which is written on this second digit here. So it has only 8 choices. And that's it. Those are pretty much the only 2 cases. So that would establish that a sub n is equal to 8 a sub n minus 1 plus 9 a sub n minus 2. I wanted to show these two different recursions which describe the desired result for the following reason, because there's two different ways you can come up with a closed form formula depending on how you constructed your recursion. The unfortunate thing on this case is you need to also calculate a sub 3. We only calculated a sub 1 and a sub 2 so far, right? So a sub 1 was 4, a sub 2 was, I believe, 32. If you want to just convince yourself that this formula is indeed true, you need to also calculate a sub 3 first by just exercising your reasoning skills, and then you can then based on that you can say, hey, this formula makes sense. But take for granted that this is the case, that this indeed works. So once you calculate a sub 3, which I totally forgot what it was, but anyhow, okay, back to our problem. So now the closed form formula, right? So because that's pretty much what the question is asking. I don't think the question, the way it's formulated, is asking for a recursive way to describe the whole thing. Instead, well, it turns out the second one, this method here, this recursion is much easier to solve. Well, not exactly much easier. Well, I mean, it's if you know the technique, it's relatively easier to solve using the characteristic polynomials, and especially if you've taken a differential equations class, it's significantly easier. So let me go ahead and solve this recursion first, and then I'll go ahead and first the very first one as well. So for this one, well, the characteristic polynomial associated with this, I can first move everything to the left hand side, right? So minus a like this, minus 9a sub n minus 2 is equal to 0. At that step, we will replace a sub n with c to the power n, right? So the reason it is that all this is in linear form difference equation, and we have only integer coefficients, and there's no other additional term. So the solution is based on the roots of this, and you will just see it in a minute that the solutions will come up in that form. So this would, once you replace an with c to the n minus 8 c to the n minus 1 minus 9 c to the n minus 2 is equal to 0. We can divide both sides by c to the n minus 2, assuming that c is non-zero, c not equal to 0. So dividing it by c to the n minus 2, we would get c squared minus 8c minus 9 is equal to 0. And now the characteristic roots are c minus 9 and c plus 1 is equal to 0, and suggesting that c is equal to 9 or c is equal to minus 1. That suggests that the closed form formula for our recursion here is a sub n is equal to, well, all that is left is to identify the coefficients. So let's call the coefficients alpha and beta. Alpha times 9 to the power n plus beta times minus 1 to the power n. And now we can go ahead and substitute the initial conditions that we had earlier to wrap up the problem. So a sub 1, I should say, which is equal to 4. Let's write it like this. A sub 1, okay, so it is 9 to the power 1, which is 9, so 9 alpha plus minus 1 to the power 1 is just minus 1, so minus beta actually. So let's minus beta, or if you plug in 2 into that formula, let's make a line here. A sub 2 we calculated earlier was 32, and that is just plugging in 2 here, 81 alpha, plus this time, plus beta. Oh, you guys can easily see that we can just add up these two equations. The betas will simply cancel, and we will end up having 90 alpha is equal to 36, meaning dividing both sides by 18, we will get 2 over 5 for alpha, and plugging it back into one of the equations, beta would come out as 9 alpha minus 4. 9 alpha is 18 over 5 minus 20 over 5 minus 2 over 5. There you go. So therefore the closed form formula, so just plugging the values into this one, so therefore we found one way to solve this problem. So we have 2/5 times 9 to the power n plus minus 2/5, or minus, let's just put minus over there, minus 2/5 times minus 1 to the power n. And if you will, we can further factor out 2 to the 5. So if you factor 2 to the 5 out, 2 over 5 out, so that's it. That will be the closed form formula for this recursion, right? So it's pretty good. Now let's go back to the very first statement. In the first one, it's slightly different, the situation. We have a recursion, fine, right? So an depends on an minus 1, but there's an additional function here, which is kind of, it requires a little bit more knowledge of difference equations or differential equations. So if you don't want to dive into these intricacies dealing with differential equations, there is a couple of different ways you can handle this. The first one is you can repeatedly substitute into the, like making repeated substitutions using A1, finding a formula for A2, and then using A2 finding a formula for A3, and so on, and then trying to seek a pattern. And once you get the pattern, we can try to prove it using induction. Okay, so for that, let me just open some space here, and let's just quickly do it next to it. Let me maybe change my color here. So let's do it. So A1 we already calculated was a 4, so A sub 2, let's recalculate A sub 2. So A sub 2 based on this formula will end up being 4 based on this formula, 4 times 9 to the power 2 minus 1, 4 times 9 minus 4, which I can factor out the 4, and you'll see in a minute why I'm doing that. Now let's calculate A sub 3. A sub 3 will be again using this formula, 4 times 9 square minus this monster, 4 times 9 minus 1, which again, factoring out the 4's one more time, we get 9 square minus 9 plus 1. You guys see that? Let's do A4. Similarly, A sub 4 is 4 times 9 cubed minus pretty much what A3, right? A3 is just this monster, so 4 times 9 square minus 9 plus 1. But hey, once you factor out the 4, again, what will be left is 9 cubed minus 9 squared plus 9. So these signs alternate. Do you guys see that? And that's it. At this stage, I think you guys can see the pattern and are ready to make your guess. A sub n will be equal to 4 times, okay, let's make a guess, 4 times 9 to the power. So whenever this one is a 4, this one is 1 less than that, so I will start 1 less, and then alternate the signs, right? N minus 2 plus 9 to the power n minus 3 minus ... And then here it will be plus minus 1 raised to the power. So for the coefficient of 9, it's plus, as you can see, if it's an even here, and it is minus if it's an odd here. So we can just say it's plus if it's an even, so we can just put it like this, and then 9, and then for the last term, again the same story, plus minus 1 raised to the power n plus 1. How about that? And if you will, yeah, that makes sense. Now what's left is to calculate this monster. So this monster is simply equal to, okay, let me erase that. Let me give a little bit more space here. There you go. This is equal to, I can factor out 9 to the power n minus 1. 4 times 9 to the power n minus 1 is out. So we have 1 minus 1 over 9, I guess, right? 1 over 9 plus 1 over 9 square. Do you guys agree? Minus ... plus minus 1 to the power n. Because we factored out 9 to the power n minus 1, there's only 1 left here, so that would give us 1 over 9 to the power n minus 2 here. And last one would be minus 1, oops, that's a minus 1, raised to the power n plus 1, 1 over 9 to the power 9 to the power n minus 1. Now I can go ahead and rewrite it in the following form. Oops, 4 times, okay, so this one would be 1 plus minus 1 over 9 plus, that's over 9, minus 1 over 9 square, and so on, plus dot 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 plus. Alright, so here I can split that minus 1 to the n as minus 1 square, which is just 1, so times, okay, so it will give us minus 1 over 9 and minus 2, and then last one I can do the same trick, minus 1 over 9 and minus 1. Okay, so this is a partial geometric sum. Oops. So therefore there's a minus 1 here. Alright, so there's times. This thing is just well, it's just 1 minus 1 over 9 here in the denominator. The numerator will simply be 1 minus 1 over 9 raised to the power 1 more than that guy, raised to the power n over there. Okay, let's do it in 2 steps. We're almost done here. Okay, so that, let's continue here. So 4 times 9 to the power n minus 1. Like I said, the denominator would be 10 over 9, and here in the numerator I'm writing this as, well, I find the common denominator, so that would be 9 to the power n minus 1 to the power n, all divided by 9 to the power n. Alright, there you go. And finally that is going to give me, well, the 9 and the 9 to the n will cancel, so that would be 9 to the n minus 1, and then they will cancel with this guy, so these 3 are gone. 4 over 10 is just 2 over 5, and what's left here is again 9 to the power 10 minus 1 to the power n. That's it. So this is 2 over 5. 2 over 5. I think it's exactly, so this is a sub n, and that is exactly the same as the very first one which we found. Let's see over here. Yes, there's only one thing here. It seems like there was some leap of faith here, right? That we said the pattern continues in the following way. You can try to use your argument to try to describe what process is going during this phase to explain, or indeed you can start with this as your guess, with this closed form, and now you can use induction to actually prove that this statement is indeed true. That would be one extra step for you if you want to finish the question. Let me, if you guys want one more, so using induction means you need to assume this is true and show a sub n plus 1 is equal to 2 over 5, 9 to the power n plus 1 minus 1 raised to the power n plus 1. So all you do is start with the expression for a sub n plus 1, which is just the recursion formula, this one. So 4 times 9 to the power n minus a sub n, 4 times 9 to the power n minus a sub n, but we assume that this is true, so we can replace it. 4 times 9 to the power n minus 2 over 5, so for an 9 to the power n minus 1 to the power n, and now bash this thing to try to see if you can come up with an expression like this, which shouldn't be too difficult. It's just a matter of just doing the right bashing. So obviously these terms are kind of very like, so we can find the common denominator. So this is 20 over 5 minus 2 over 5, so this is 18 over 5. 18 over 5 times 9 to the power n, and we still have minus, so it's plus 2 over 5 minus 1 to the power n, and that's just 2 over 5. So this has a 9 inside, so I'm moving it to the other side, and you know what, I'm going to multiply both this and this by minus 1, so that would give us minus 2 over 5 minus 1 to the power n plus 1. Aha, and that's exactly what we needed to show. We needed to show this expression, and we have exactly the same expression, and so this shows by induction that this statement is true. That's it. So this was like I said, so the first part of the problem where you do the actual counting was relatively straightforward. We provided 2 different methods for doing the counting by using recursion. The second part required a little bit more advanced knowledge of solving difference equations, or at least establishing a pattern initially, and then once you have the pattern established, make a guess for that closed form formula, and then use induction to finish the proof, basically. So both of them are legit methods to finish the problem. Hope you enjoyed this. Looking forward to see you guys in our next lecture.